We're going to solve this problem using calculus techniques. You have 40 yards of fencing to enclose a rectangular region. One side is along a building and will not require fencing. Find the dimensions that will maximize the enclosed area. What is the area? Let's draw a picture. For this picture, we are building a rectangular region that is along the side of a building. So we have some building, and we're building a rectangular region along the side of that building. We don't need any fencing along the side of the building. And our goal is to maximize the area that is enclosed within this fence and along the building. So I'm going to label the sides of our rectangle with W and with length, and the area of this enclosed region would be length times width. So this is our primary equation, and this is the equation that I want to do the calculus techniques on. But at the moment, I have too many variables within my equation. So I want to use other information in the question to try to reduce the number of variables. So we have 40 yards of fencing. The fencing is going to go up along these three sides, and that means that our 40 yards of fencing should equal the length plus 2 times the width. I can solve for either length or width and then substitute into my area function to reduce the number of variables. In this example, I'm going to choose to solve for the length because it doesn't have a coefficient. Although solving for width is a valid way of doing the problem, I would eventually have to divide by this coefficient, and I would have a fraction within my equation. So just to avoid that, I'm going to solve for the length. I'm going to subtract 2 times the width on both sides. This gives me the length equals 40 minus 2 times the width. And I'll be able to substitute this in for the length. This is going to give me an area of 40 minus 2w times w. And I'll use the distributive property since I'm going to be using doing the calculus techniques on this. I want it in a simple format. So that's 40w minus 2w squared. And now that I have my area function in terms of just one variable, I'll start solving with those calculus techniques. So I'll calculate the derivative. And the derivative would be 40 minus 4w. I'm going to set that derivative equal to 0 to get the critical numbers. And I can solve this equation by adding 4w to both sides. I would have 4w equals 40. Divide both sides by 4 to get w equals 10. And this is my critical number. I want to determine if this critical number is a maximum or a minimum. Remember, I'm trying to maximize the area. So I'll calculate the second derivative. The second derivative would be negative 4. And since my second derivative is always negative, that tells me that this function is concave down. And concave down, along with the fact that 10 is a critical number, tells me that I have a maximum value, which is what I was looking for. So we want to know the dimensions that will maximize the enclosed area. So we have found that w equals 10. We can use this equation here to find the other dimension of length. Length is 40 minus 2 times 10. That's 40 minus 20, which is 20. So the dimensions of our rectangle will be 10 yards by 20 yards. Those are our dimensions, and our area will be 10 times 20, which is 200 square yards. So the maximum enclosed area is 200 square yards, and we achieve that with a width of 10 and a length of 20. For this question, we're given the function g of x equals x to the 2/3 in the interval from 1 to 8. And what we want to do with this function is we want to determine whether the mean value theorem can be applied for this function on this interval. If that theorem can be applied, then we want to find all values of c guaranteed by the theorem. Let me give you the statement of that theorem so we can take a look at it. And with the mean value theorem, we need our function to be continuous on the closed interval from a to b. We also need it to be differentiable on the open interval. And if we have those conditions met, then we know that there exists some number c in the interval from a to b, such that the derivative at that value of c is equal to f of b minus f of a over b minus a. So if you'll recall, this left-hand side of the statement of the conclusion represents the derivative at a point, which is the slope of the tangent line. And then the right-hand side of the statement is the slope of our secant line. So what we're saying is that as long as our function is continuous and differentiable on the interval, then we will have this value of c somewhere on the interval where the derivative at that point, the slope of the tangent line at that point, will be equal to the slope of the secant line. And we're using a and b to create the slope of that secant line, which are the endpoints of the interval. So let's take a look at this function to see if the conditions are met. So first of all, we have the condition of being continuous. Our function g is g of x equals x to the 2/3 power. X to the 2/3 power is the same thing as the cube root of x squared. And I know that the domain of an odd radical function is all real numbers, and that we will have a continuous function on the domain. So because the domain is all real numbers for this function, the function will also be continuous over all real numbers. So certainly, since it's continuous over all real numbers, it will be continuous on the interval that we're interested in, which is from 1 to 8. Then the second condition is that this function needs to be differentiable. I mentioned earlier that some radical functions have places where they're not differentiable. So I wanted to show you a picture of this graph. With our calculator, we've got y. We'll type in the equation x to the 2/3 power. Sorry about that. Let me fix it. X to the 2/3 power. If we take a look at that graph, what you're seeing, let me zoom in a little bit. What you're seeing right there in the middle is something that we call a cusp. And that value where the cusp is a spot where this function is not differentiable. It's not smooth. It's coming to sort of a sharp turn. This is in this case, a cusp, and so the function will not be differentiable at that point. But as you can see by this picture, that value where the cusp is, that value where the function is not differentiable, is at x equals 0. So going back to our interval here, what we're saying is that although this function has a spot where it's not differentiable, so let me write that out, g is not differentiable at x equals 0, but our interval is going from 1 to 8, and 0 is not in that interval. So even though g is not differentiable everywhere, on the interval that we're interested in, it is differentiable. So g is differentiable on the interval from 1 to 8. So this function has met the conditions of the mean value theorem, and we can proceed in finding that value of c that is guaranteed by the theorem. So to find the value of c guaranteed by the theorem, we're going to calculate the right-hand side, which is that slope of the secant line. We're going to start calculating the left-hand side by calculating the derivative, and then we'll set those guys equal to each other and be able to solve for that value of c. So let's calculate the right-hand side by finding g of a. G of a would be g of 1. That's 1 to the 2/3 power, and that means the cube root of 1 squared, the cube root of 1, which is 1. And then we'll find g of b. G of b is g of 8. That's 8 to the 2/3 power. That's the cube root of 8 squared. I think it would be much easier if I did the cube root first, cube root of 8, and then square it. The cube root of 8 is 2, and 2 squared is 4. So then we'll calculate g of b minus g of a over b minus a. That's g of 8 minus g of 1 over 8 minus 1. G of 8 was 4. G of 1 is 1. 8 minus 1 is 7, so we've got 3/7 here. And we'll calculate the derivative. So remember, our function g of x is equal to x to the 2/3 power. We'll calculate the derivative using the power rule, and that gives me 2/3 x to the negative 1/3. And I want to set the derivative equal to that value of the slope of the secant line. That's 2/3 x to the negative 1/3 equals 3/7. I can start solving this equation by multiplying by the reciprocal. That's 3 over 2. So on the left-hand side, we have x to the negative 1/3 equals 9 over 14. X to the negative 1/3 is the same thing as 1 over x to the 1/3. So I could cross multiply to solve this. That would give me 9x to the 1/3 equals 14. I'll divide by 9, and that gives me x to the 1/3 equals 14 over 9. Remember that x to the 1/3 power means cube root of x. And so to solve, getting rid of the cube root, I would cube both sides. That gives me x equals 14 cubed over 9 cubed. Let's see what that comes out to be. 14 cubed is 2,744. 9 cubed is 729. 2744 divided by 729 gives me 3.76. I'm just rounding to 2 decimal places. So this would be our value of C, and before we finalize this, I just want to verify the interval that we have for this question. If you remember, was the interval from 1 to 8, and 3.76 does lie in that interval. The value of C guaranteed by the mean value theorem is 3.76. Thank you for checking out my videos. Have a great day.